Alrighty, more sequences. Let's get into some terminology. Let's talk about some terminology. Oh, there's a lot of it. We gotta have these pieces down. So, increasing. And when we're saying increasing, it's always increasing. Like, see, 0, 1, 2, 3, 4, 5, 6, 7. It's increasing. So we can talk about it and be like, oh, we have an increasing sequence, which means it's always increasing. No counterexamples. Now, what does non-decreasing mean? Does that mean it has to... Non-decreasing. Does that mean it has to increase every time? No, it just means it has to never decrease. So as you can see, from the first term to the second, it doesn't increase, but it sure as hell doesn't decrease either. So this is non-decreasing. Doesn't mean non-decreasing, does not mean increasing. It just means it's not going to do that, right? Like when I say negative numbers, it doesn't mean the opposite of negative numbers is positive numbers. The opposite is actually 0 and the positive numbers. Same sort of idea. So non-decreasing means it just doesn't decrease. It doesn't mean that it always increases, though. Now, if it's decreasing, well, it needs to decrease. All those numbers are smaller. Every term has a smaller previous term. Or each term decreases. Let's just go with that. Non-increasing, same sort of idea as before, right? Non-increasing means it just doesn't increase. Doesn't mean it has to decrease for every term, right? 0, then -1. Look, it doesn't decrease. But it sure as hell doesn't increase either. Now, monotonic. Ooh. It's monotonic if it is either non-increasing or non-decreasing. It just means it moves in one direction. So non-decreasing and increasing, these two together, means that it is monotonic. It's only going one direction. It's getting bigger. Maybe not every term it's getting bigger, but it's getting bigger. Similarly, it's monotonic if you have decreasing or non-increasing. They're both moving in the same direction. They're both getting smaller eventually. And then we're going to talk about something called a bounded above. There's a number n such that a sub n is always less than or equal to n for all relevant values of blah, 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 bullshit, bullshit, bullshit. Hey, you remember this? Let's talk x's. Y is equal to inverse tangent of x. This is both bounded above and below. Now, I'm talking about a continuous function, not a discrete function like with n's. But we would say that this is bounded in between -pi/2 and pi/2. Saying it never gets bigger than pi/2. Never actually achieves pi/2. It's going towards it as our limit as x tends towards infinity. And it never gets smaller. It never even equals -pi/2, but it's going towards it. That's what we call bounded above and below. So it's saying our m here is pi/2. That little m. And then they're saying some n it needs to be bigger than. Well, our n is -pi/2. That's what it means to be bounded above and below. Now, and not all functions, so usually it's just a bounded above or bounded below. Usually not both, but I gave you an example of our last piece where we say it is bounded. So inverse tangent of x is actually completely, we don't even say bounded above or below, because it's bounded, it's stuck in between two different numbers. So there's times where it's just bounded above. Sometimes it's just bounded below. We're going to see a few of them. So let's try one. And let's start off with something that's reasonably mellow. Let's look at these two. Let's say we got some a sub n, which is n to the 5/2 power over n to the 5/2 power. Plus, let me put in 6. And then we're going to have some b sub n we'll mess around with. And on this one, let's just change it up and give it a -1. But let's make everything else the same. N to the 5/2 power, n to the 5/2 power, plus 6. All right, neat. Neat. Okay, so let's talk about a sub n first. We're going to want to find what's the limit as n tends towards infinity of our a sub n. What's that going to equal? But let's talk about a few things with it. Well, it's always positive, isn't it? It's always positive. It's always increasing, too. I'm skipping over plugging in all the frickin' numbers. But it's always positive. And it's going to be bounded. How do we know this? How do we know this? Whatever. Let's see what happens. Let's plug it in. Let's just see what we get. So the limit is n tends towards infinity. Now, are we only plugging in positive numbers here? And then we're only adding a positive number down here? I think that makes it positive. You know what I mean? You know what I mean? So it's positive, it's increasing, and it's bounded. All right, well, let's run through it. And we don't have to have all of this super down, like, I have all my terminology down. We got to be able to do the gosh darn limit. Now, we have the same degree, top and bottom. Top and bottom, same degree. 5/2, 2.5. So really all we got to do is just look at the coefficients out front. But I mean, if you don't want to recognize patterns, we're like, okay, well, let's do L'Hopital's instead of just stating the gosh darn answer is 1. So we're like, all right, well, what's the derivative of n to the 5/2? Well, it's 5/2 n to the 3/2. Okay, done. Now we go down to the bottom. We're like, well, we got to take a derivative on n to the 5/2 plus 6. So that's going to be 5/2 times n to the 3/2. What's the derivative of 6? Oh, yeah, that's fricking nothing. That all cancels out and we get a 1. If you were to have graphed this, well, your numbers would have looked a little something like this. 1, 2, 3, 4. And then they would have got a little closer. And then we got a little closer, a little closer. And we kept going. We get all these dots. And where we're going to is 1. It's just getting closer and closer to 1 as we move through. They're just going towards 1. So this is bounded above by 1. It's bounded above by 1. The limit goes to 1. But what about that second term? We can't play these same limit games. I know kind of where it's going. I can't really do the limit because how the hell are you supposed to deal with this? How are you going to deal with that negative 1 to the n? What are we going to do? What are we going to do? We have tactics. Smart old dead dudes came up with some stuff we're going to learn about. We'll do those in sections as we go on. But if you were to begin looking at these terms, how the graph is going to go, let me draw this one out a little differently. Let's just call that like 20. We'll call this one 10. And well, our first term would be negative. This would be negative 1/6. And then our next term would be positive. The next one would be negative. And we'll start doing this. We get closer to 1 up top, and it's getting closer and closer to negative 1. So it's going to do one of these. But look, they're going to two different heights. So the limit's not going to exist because it looks like the limit of all of our positive outputs is going towards 1, and all the stuff from our negative outputs is going towards negative 1. So the limit won't go there. It's not gonna converge to a number. But this sequence is bounded between negative 1 and 1. Can never be smaller than negative 1. Shit, it can never actually equal negative 1. All of our values, shoot, I shouldn't write like this. Did I write that? Oh, it's trapped between negative 1 and 1. So it's a bounded thing. And we're just kind of learning a little bit. Even if you didn't catch up, did you just see that there's a freaking negative 1 right there? Which is going to change the sign where it's always going to go back and forth, 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 back and forth. Cool, you learned something. Woo, good job. So that's going to be just the terminology. Increasing, non-decreasing, decreasing, non-increasing, monotonic, bounded above, bounded below, and just bounded. So we want to make sure that we have that terminology down because once it pops up on a test and they say like, hey, is this thing bounded above or below? You know what it means? your host. So we want to make sure that we get this terminology down, but I think you'll get it naturally just by doing problems. See you.